Hello, Tensor friends. I got asked a question. Can I explain the first and second fundamental forms? And my answer was no. Then I said, well, I need to learn this. So I did. It turns out we know one of these. We just don't call it this. This is very old terminology. It goes back to the father of differential geometry, Carl Friedrich Gauss, in 1825, 200 years ago. All right, let's get rocking. So, the first fundamental form, we're going to take an example. So let's take a paraboloid. Z equals x squared plus y squared. It looks like this. Okay? And it passes through the origin. That's important for later. Alright, so we're going to parameterize the surface of this with u and v. This is a very normal way to do this. So x is equal to u, y is equal to v. We plug those in, we get z is equal to u squared plus v squared. Alright, now we take the infinitesimal line element, which in the Cartesian the coordinates is the same as the Pythagorean, the theorem. Alright, and we plug all this in. So dx is just du, dy is dv, and dz is 2u du plus 2v dv. Alright, so we're going to now square all that and put it in. So just du squared plus dv squared. Then we square this, so we FOIL it. We get this expression. We gather up all of our terms, so the du then is 4u squared plus 1. We got this term by itself, and 4v squared plus 1. Alright? So here is our infinitesimal line element parameterized on the surface of that paraboloid. Alright, now here's the way he wrote, I think, the first fundamental, the form. He would say that this coefficient, that coefficient, and this coefficient are E, F, and G. So he would take half of this, which in our case is obvious. It's just 4. So this is the matrix, in a matrix, the form of what it would look like. Okay? So we got E, F, because it's symmetric, and G. So we know what that is because we do it in modern times like this. The invariant infinitesimal line element ds squared is equal to the metric tensor times the product of the infinitesimal components, right? So we're only working in 2 dimensions, so we're going to have 4 of these, and we would write them like this: guu du squared plus guv du dv plus gvu dv du and gvv dv squared, right? So we need this. So what we would do on that paraboloid, we would define a position vector r, which has x, y, and z components and the orthonormal basis of the vectors here. Then we put in our parameterizations. All right? So x is u, y is v, and z is this. Now we need to find our EU and EV basis vectors. And we've done this many, many times. So the EU basis vector is the derivative of that position vector with respect to u, which is just 1 here, and 2u EZ here. And D and EV is the derivative of this position vector with respect to v. So it's just 1 and then 2v EZ. Alright? So now we can find our metric, the tensor. So it is just EU dot EU, so EU squared, which gives 1 plus 4 u squared. Remember, EX dot EZ is 0, EX dot EX is 1, EZ dot EZ is 1. So we get a scalar. GUV is EU dot EV, which is 4UV, and it's a symmetric tensor. It always is. I shouldn't say always. Everyone I've ever seen is symmetric. 4UV, 4UV. And then the last one is EV dot EV, EV squared, and we get this. All right? 1 plus 4v squared. So now we got our metric, the tensor, And we can put that right back in to our equation here, and we get exactly the same thing, except remember now they go 2f, so it's half of this, but it's the same thing. So this is the modern way we would do it, and this is the original way he would write it, I think. It's very hard to find all this old information. All right, so we knew what the first fundamental form was. We just call it something totally different. Now this one is new to me, okay? The second fundamental form, it is passing a plane through the surface you're studying, okay? And this plane, you notice, passes through the origin. And now this is going to give us two curvatures, that curvature and this curvature. Obviously, because this is a paraboloid, it's the same curvature, but in all cases, in some cases, it's not. All right? So I'm going to use the terminology that they used, okay? So we still got our same position vector with this parameterizations, and they would write, I mean the old guys, they would write r sub u is the partial derivative of r with respect to u, which we called eu, the basis vector. And I'm going to write down the way the mathematicians would for the vector, which would be 1, there's no y component, and the ez is 2u. We're going to need this later. And ev, they would write the same way. Okay, so it'd be 0, 1, 2v. Now, the second derivative, ruu, the second derivative of this with respect to u, would just be 2ez, right? And the second derivative of u with respect to v is 0. There's nothing there. And the same thing is true here. There's nothing there. And the second derivative of rv with respect to v is just also 2z. All right. Now, he defined these letters, L, M, and N, as the dot product of these second derivatives with respect to the surface normal. All right, so let's go look at that. Okay, I'm in desmos.com/3D. Now here is the vector that we found. Remember 1, 0, 2u, so we're just going to call that R1. Here's the other vector we found, 0, 1, 2v, remember? So we got two vectors. Now if we take the cross product of those, we find the normal to that plane that passes through those two vectors. Do you see that? And the magnitude, stop it. I hate it when it does that. The magnitude of this is equal to the area of this parallelogram that these two form. And that's not important to us. Now, this is just the normal vector. It's not the unit normal. If you needed the unit normal, you would divide this vector by its magnitude, and it would look like that. And we don't need that because it complicates the equation and it all turns out in a wash. Okay? Okay, so here's where we were. He defined this L, M, and N as the dot product of these second derivatives with respect to the normal. He actually used n hat, but I'm not going to do that because it made it more complicated and it worked out this the same way anyway. So we need to do the cross product of RU dot RV, okay, to find this normal. And we know how to do that, remember? So in your mind, you cross out this column and this row. So it's this times this minus that times that. So it's a 0 minus 2u. And that's our EX basis vector component. Block out this column and this row. Write down a negative, wicked important. It's determinant of this matrix, 1 times 2v minus 2u times 0, just minus, so we got the minus there, 2v. The last one, you block out this, and this will give you your EZ components. It's just 1 times 1 minus 0, just 1. Okay, so now we got our normal. So we have to cross each one of those, the second derivatives with the normal, and that's easy, it's just 2. The second one is 0, because that's 0. and the last one is 2. Okay? So now we have the second fundamental form matrix, and they write it like this: L, M, M, symmetric, and N. All right, now what can we do with this? The Gaussian curvature, one of the definitions of it is K is equal to kappa 1 times kappa 2, where kappa is called the principal curvature. Okay, and it is just the determinant of this, the second fundamental form. So kappa 1 is 2, kappa 2 is 2, so the curvature is equal to 4 at the point 0, 0. So this is giving you the curvature. Let's go all the way back to that picture here. This is giving you the curvature of this paraboloid. So this would be kappa 1, that would be kappa 2. And obviously they're equal, right? So the total Gaussian curvature at that point, now this is important, is at that point is 4. For whatever good that is, I'm not sure, but it's 4. Okay. Now there's another definition of the Gaussian curvature, which is the determinant is equal to the determinant of the second fundamental form divided by the determinant of the first fundamental form. All right. So we need to go back to our first fundamental form, which was this, and take the determinant, and we know how to do that. It's this times this minus that times that. All right, so we get this minus 4 fours is 16. We get u squared v squared. We FOIL this, and we get this expression. Luckily, that cancels that, and we're just left with this. So now let's put it all together. So this is the determinant of the first fundamental form. We put it back in our equation, and we get 4 over this. Well, you're saying, well, that's not the same as what we got a while ago. Well, it is at the point 0, 0. If u equals 0, v equals 0, then big K is equal to 4. This would be the generalized form where I could find the curvature at any point on that paraboloid. That's the point. That's the point of this. Okay, at any point I can find the curvature. All right, wasn't that fun? I'll see you later.